That's not secure, and that's not secure. That one's not secure either. That one's definitely not secure. One way or another, it turns out there really isn't a truly secure chatting or messaging app. And that's because all of these companies, all these tech giants, they're doing it wrong. Okay, rapid fire questions round. What's the least secure message? A plain text one. Anyone can read it and know what it says. What can make it more secure? Encrypting it. Only the sender and receiver knows what it says, and everyone with access to a key to decrypt it. What can make it more secure than this? Not sending it. I mean, the only way to know for sure it's not gonna get leaked is not sending it. So that's what I'm doing. A chatting app where no messages are sent. Of course, there is a data transfer, but at no point in this app's flow is a step where the message someone wants to send even touches a network connection or communication channel. It just stays safely tucked away on their local machine and lets this thing I created do its magic. Now, the key word in this project is compression. More specifically, Gzip. But what even is Gzip? Well, it's a file compression format that's been around since the 90s. It uses an algorithm called deflate, which is basically two tricks combined. First, finding repeats. If you have the letter A written 6 times, instead of storing 6 individual A's, it just stores 6 times A. And second, Huffman coding. Common symbols get shorter codes, rare ones get larger ones, making the overall size smaller. And because of these two characteristics, if you have strings with many repeating characters, they end up really compressed. Whereas if you were to, say, generate random noise, it couldn't do much compression at all. So if a string can either be compressed or not, that's a true or false statement, right? In shorter form, it can be expressed as 1 and 0, which is very much just a bit value. Starting to see where I'm headed? Normally, when you talk to a server, you formulate the request by setting a method, path, adding some headers and the body. But what if instead of the request containing the body is instead composed of the requests? What if I take the string I would normally send via a post request to a server and instead send its individual bits with separate requests towards the server? Obviously not sending the bits as is, but instead express them using compressed versus not compressed messages sent to a server. So that if a request's payload gzips to a really small size, that's a 1, and if it doesn't, that's a 0. Now, it's not like there's a big label that says compressed enough or not, just like a switch. Instead, a threshold needs to be set, so that whatever is below it is deemed as compressed and what's above as not compressed. Of course, if you just eyeball the threshold, sometimes the random payload might sneak under the line and look like 1 or vice versa. And you also gotta take into consideration that compressed sizes don't come out exactly the same every time. It depends on stuff like input length, zlib's behavior, network architecture, and many more. With a properly calculated threshold, it can draw the line between definitely compressible and definitely random, with high confidence no matter the environment. So you also have to calibrate it as a preliminary step between client and server, our very own custom handshake. It goes like this. First, the client sends one very compressible payload, and then one very incompressible payload. Then the server measures both their compressed sizes and returns the results. And last, the client calculates the threshold, in our case the average of the two lengths, and then notifies the server. That way, both the client and the server agree. Okay, below 80 bytes, that's a 1. Above, that's a 0. Okay, so now there's a way to encode and decode individual bits. Time to bind them together properly. The message itself is structured like this: a header of 16 bits where its length in bytes is described. Of course, you can allocate more bytes, but do you really want to send more than 500,000 worth of requests messages? Then the message itself as bits. And last, a checksum so that the server can verify the integrity of the message. In this case, it's just an exclusive OR of all the message's bytes. This way, the server knows how many requests it needs to read and checks they were all properly received after they're all successfully sent. And on the other side, the client has a really long list of 1s and 0s to transform into HTTP requests. Now, for simplicity's sake, each request is either the letter A repeated a bunch of times for 1 and a completely random string for 0, so both at the very edge of the compression spectrum. If you actually wanted to fool someone, you'd make sure these requests were a lot closer to the threshold. Maybe even ensure they were legible messages on their own, so someone could think they were reading your actual chats. Aside from the payload, the headers are also crucial here. Thing is, networks are not stable things. Same with communication channels. Messages can and will show up out of order, relative to how they were sent. So we've got, first off, X client ID, a unique name for the person or program sending the message. Then X frame, which is the ID of the message you're currently sending. A client may send multiple messages in one session. X-frame keeps them separate so the server doesn't accidentally glue together the bits from high and bye into high bye, for instance. And last, exsec, the sequence number of this bit in the current frame, aka message. Now, with the message built and on its way, the server has the task of properly reconstructing it. For each request received, start by reading the headers and use the combination of the client ID and frame number as the key for the registry in which each entry is a bucket that contains a message either complete or in the process of being constructed. This bucket is pretty much an array that stores individual bits, where the index corresponds to the sequence number of the request. Then, compress the payload and see if it's below or above the threshold. Also, I forgot to mention, but you can customize the compression algorithm however you like. Just make sure to keep it constant, starting from the handshake step. The more you customize it, the harder for someone to guess what the threshold actually is. Pair that with making the payload messages as natural as possible and boom! Codified messages hidden in plain sight. Separately, the server will have a constant worker that checks if any buckets are full, meaning a message is fully sent, validated, and ready to be decoded. This is done by first checking if the length of the message matches the one sent by the first 16 bits. If true, then compare the checksum with the exclusive OR product of all the bytes in the bucket, minus the first two and the last one. If that check passes too, the bits can just be converted to bytes and then to a valid string. So, for a short step-by-step of how this entire flow goes, first the user types hi. Each letter is then transformed to their bitwise representation. Next, we know the message's length is 2 bytes, and the checksum is 1. In total, the message is 40 bits, so 40 requests to be made. Now, for each request, set the headers for the client ID, say Bob, the frame ID 0 because this is the first message sent from Bob, and the sequence number, the index of the bit in the message. Let's also say 0 because it's the very first request, and then set the body depending on the represented bit value. The server now takes this request and compresses the body to get the bit value. Then, in the registry, at the key Bob0 sets the bucket at index 0 as the bit's value. This is then done for each individual request. Meanwhile, the separate worker in the server regularly polls the messages bucket. So when it finds a bucket whose message length matches the number of bytes in the message, and the checksum matches the exclusive OR product of those bytes, it converts the message bytes into the string representation, getting the hi. Here's how it looks with a longer message. Huh, cheeky client. Of course, you could go a step further and have the message itself be encrypted before all these steps happen, and have the information required to be decoded, like a key pair, to be shared in the handshake step. Oh, and also obfuscate the header values. This way, even if someone by some accident or miracle first recognizes that seemingly normal-looking messages are actually hiding something using encryption, correctly guesses the exact value of the threshold, deciding if a message is compressed enough or not, de-obfuscates the header values and somehow reconstructs the message using its bits correctly, they would still need to decrypt the contents to actually get anything out of it. Of course, it's not perfect, but security never is. However, I'd say it's pretty damn hard to crack. And the only downside is a ridiculous number of requests that would make even tech giants shake in fear of a DDoS attack. But that's just a computing power issue. We'll surely get hardware good enough in a couple of years.